All right. Oh. So. Okay, we talked about S values, we got excited about that. Or Bayes factor, right? Am I correct? This is where we ended up last time?
So the Bayes factor and BFB.
Yeah. Okay. Okay. All right. So finished up talking about complementary statistics, talked about our S values, and then introduced this possibility of this Bayes factor business here. And again, the idea is that, as we talked in the previous lecture, that our p-values don't really answer the question that the scientific question that we want to answer, right? What we want to know is how strongly does our evidence favor our alternate hypothesis as opposed to our null hypothesis, right? What do our hypotheses tell us? What's our formal interpretation of that p-value, or what's our conclusion? Do you remember, Emily? Yeah.
The manipulation having an effect.
That what?
That effect. Like, the manipulation had an effect.
Okay, so that's what we conclude.
Okay.
But what does our hypothesis test actually tell us? What do you think, Basha? Whether there's a difference? Okay, again, that's what we want to know, right? Thinking back to that is, I was waving my hands around, talking about everything that's wrong with our whole approach to testing. What does our hypothesis test actually sort of tell us? Remember that what this is saying. Yeah, Sam. Okay, yeah. Okay, perfect, beautiful. Given that the null is true, assuming that there is no effect, assuming that there is no relation, assuming that there is no difference, what's the likelihood of obtaining data with these characteristics or more extreme, right? So assuming that the null is true, how likely is it that we would obtain data with these characteristics? And that's what our p-value is telling us, right? And again, thinking about p as a measure of the incompatibility of the data with the null hypotheses, assuming that all of our null model and all of our ancillary hypotheses are all valid, which there never are, right? And so that starts to become problematic. But again, our hypotheses are testing a question that's not the question that we're actually answering. What we want to know, right, is the strength of evidence question. So based on the data I'm seeing, what's the likelihood of my alternative hypotheses? What's the likelihood that there is a difference, right? Problem is, that's not what our test is telling us. It's saying, assuming the null hypothesis is true, how likely is it that we would find data of this nature? Now, if it's way out of bounds, we say these data are would be very improbable to be pulled from a distribution where there is no relationship, where there is no difference. And so then we use that to say, well, then it's likely evidence that the null hypothesis is not true, right? But as we went through, there's all sorts of problems with this, right? Because it's not a straightforward, we can't just take that probability function and turn it back and forth and have it mean the same thing, right? So this is where we get into our Bayesian statistics. I'm not an expert in this. I don't do Bayesian statistics. People who are Bayesian folks get really into this. But the idea is presenting these Bayes factors that give us the average likelihood of the data under the alternate hypotheses, or the likelihood of the data under the null, right? Now, all of a sudden, we're working with an odds ratio that's giving us the likelihood of this thing versus an alternative, okay? Now, the problem is, and this is the limitation of Bayesian statistics, is what we need to know, as we talked about or alluded to in the last lecture, what we need to know is some estimate of the probability or the likelihood of the null and the likelihood of the alternative hypotheses, and we rarely know that. That's not something that we have good data on, which starts to complicate calculation of these types of statistics. Now, one of the suggestions that Benjamin and Berger put forward is that what we might do is instead is just provide and calculate based on the p-value an upper bound of that Bayes factor, right? We can't calculate an actual Bayes factor because we don't have enough information to do that. But assuming that there's a 50-50 chance that the null and the alternate are equally likely, right? Kind of best case scenario. If that's what we assume, what we can do is calculate our Bayes factor bound. And this is going to give us an upper limit of our Bayes factor that we can calculate directly from our p-value, okay? Which is convenient because we're always got our p-value. And so we can just say, take our 1 divided by negative Bayes c times our p-value times the natural log of p. This is going to give us our Bayes factor bound, okay? And again, we're interpreting this as the largest possible Bayes factor that would be consistent with the observed p, giving us the odds for the strongest case of the alternate hypotheses relative to the null based on the data. Okay. And so now all of a sudden what we've taken is this, and in an optimal scenario, which shouldn't make us too worried because that's all we're doing with statistics is we're always assuming an optimal scenario. These are models that are assuming sort of a perfect sort of built in a vacuum, and then we take it out and put it in real life, and then all of a sudden things start to get a lot more uncertain with stuff. But if we want to go through and take a look here, so again, here's a set of p-values corresponding to a t with 50 degrees of freedom. Here's our natural, our base 2 log of p. Here's our s values, and here's our Bayes factor bound. Okay, Bayes factor bound, we can interpret these as odds. Okay. Just as a refresher, odds are representing the occurrence of event relative to the non-occurrence. Okay, so we calculate odds by calculating the number of events divided by the number of non-events, and this gives us whatever the answer here is x to 1 odds. So nice thing about odds, we can turn these into probability for an event. If we take our odds that we get and divide it by 1 plus odds, this gives us a probability of the event. If we take 1 minus that probability, we get the odds against the event, right? So there's lots of different ways we can play around with this and use these odds to draw interpretations, okay? So let's say for p is equal to 0.005, okay? This gives us an S value of 8. Amanda, can you tell me, do you remember, can you tell me what an S value of 8 means? How do we interpret that? It is something we get it with the logs. We go through and calculate that with our log function. Do you remember how we interpret that value of 8? Anybody help her out?
Like number of heads in a row in the coin toss?
Yeah. So we can think about that as pieces of information. This, if I find p-value 0.005, calculating this S value of 8 is basically saying evidence against the null with p equals 0.005 would be about the same functionally as me telling you, hey, Amanda, I got this ferret coin, and I flip that coin 8 times in a row. All times is 8 consecutive heads. After 8 consecutive heads, how confident are you that I have a fair coin? Probably not, right? You're guessing that, hey, that's probably something fishy is going on, right? Is it impossible? No, but it's starting to become like you're probably not super convinced that I have a fair coin, okay? What we can also do then is we calculate our S value. We can also go through and calculate our Bayes factor. Bayes factor bound is a 13.89, right? And so what we could say is that the likelihood, based on this, the likelihood of our alternate hypotheses is at most about 14 times that of the null. Okay, so I mean, I just kind of rounded this up, just so we're not 13.89 is probably a little specific for sort of given in uncertainty. We're saying about sort of the likelihood of the alternate hypothesis is about 14 times that of the null. How do you feel about that? That's pretty, I mean, that's answering directly, not assuming that the null is true, the likelihood of these data. This is saying, based on what we've got, we're saying that these data upper bound, like best case scenario, these data are saying that the alternate hypothesis is about 14 times the likelihood of the null or the alternate hypothesis is about 14 times that of the null. Now that's also all of a sudden starting to give us something that I can kind of work with and think about, right? We can do a lot of stuff with odds. What's even odds? What means 50-50? Two things are equally likely. What's the odds value that we get for that? Was that 1? Yeah. Even odds. So both things equally likely, right? So what we can do is recognizing that if 1 equals even odds, what we do is we take that odds ratio, subtract 1, and then just turn that into a percentage, right? So if we subtract 1 from that, we can say we could alternatively interpret this as the alternate hypothesis is 1,289 times, or 1,289% more likely than the alternate. So it's the same thing, just however you want to sort of go through and frame and talk about these. So it starts to give us a means of describing evidence for our alternative hypotheses relative to our null, which can be kind of a useful way to start thinking about strength of evidence. Okay. We could also say that there's a 6.7% chance that the null is true, assuming the alternate and the null are equally likely. How did I get this piece of things? I just used some math up here, right? I took, you have the calculators? If I take 13.89, which is my odds, and I divide that by 1 plus my odds, gives me a probability value of 0.933. And if I take 1 and subtract that, it gives me 0.67, right? Essentially giving me the percentage likelihood of the null hypotheses, right? So we can play around with these and sort of move these backwards and forwards and start working with these in ways that start to make sense in terms of how I want to communicate things. Yeah. What's that?
Like which variable represents odds?
So this our base factor. Our base factor bound.
Okay. Okay.
This is our odds. This is essentially an odds.
What is the
S values, that was what we finished with last time. This is 1 over base 2, the log base 2 of P, but then there's a conversion on there that makes it easier. So you can just use natural log to calculate that. Okay. All right. Where are we at? Okay. So the thing to remember though, and this is in that Benjamin article, remembering that our base factor is the strongest case for the alternative relative to the null. Best case scenario, upper bound of this. Base factor bound means it's the top, right? That's not saying that this is the probability. Our probability is probably, our actual base factor is probably quite a bit less than this, right? This is saying best case scenario in situations where the null and the alternate are equally likely, right? In fact, that's rarely the case. We start to get an imbalance and that starts to drive things down. So always want to take this within a grain of salt. But when we're thinking about 4p equals 0.05, right? We got an S value of 4, right? So that means I flip a coin, I hit 4 consecutive heads. How convinced are you that that coin is not fair? Maybe. I'm starting to be suspicious. But if you told me, yeah, this is a fair coin, would you be shocked? No, right? Probably not. After 4 heads in a row, like, all right, okay, then it was just a weird thing that happened, right? Same thing if we go through and take a look at our Bayes factor for 05, it's 2.46. This is saying under the best case scenario, the likelihood of our alternate hypothesis is only about 2.5 times that of the null. So again, starting to recognize that our criterion for claiming statistical significance is actually a pretty low degree of evidence against it. It seems like a lot, right? Like, boy, only a 5% chance if the null were true that I would find data this extreme or more likely. But remember that that is not the question that we're asking. If we flip that around, if we ask, so what our null is telling us is the probability of the data given the null. What we want to know is the probability of the null given the data. Those aren't interchangeable probabilities, and it's actually not the evidence that we would hope it to be. Okay, now this is the thing, like people will say, well, it's already goddamn hard enough to find effects in anything anyway. We don't want things to be more stringent. Fair enough, I agree. Cranking up the level of what we call statistical significance would probably just facilitate or encourage more sort of game playing and p-hacking and who knows what else, right? So I'm not saying that we don't report and sort of be pleasantly surprised when we sort of meet that criteria that we've decided is something that's publishable. But what we should do is recognize the strength of evidence for that and have realistic expectations of the extent to which the effect that we found is probably something that we can say is going to be realistic, consistent, things along those lines. Okay. It's like kind of a slightly sort of taking a slightly dysthymic approach to statistical analyses. Like, oh, I'm excited a little bit. Like, it could be better, you know. But sort of wanting that before we start pursuing lines of research based on one person that's found an effect that just kind of tips over the edge, and then sort of maybe making more of that than is wow. Okay, so some interpretive standards from this Cass and Rafferty for our Bayes factor. Okay, Bayes factor, and again, these are just general guidelines, right? There's no, you'll see even sort of it's 1 to 3, 3 to 20, 20 to 1 feedback. Oh, well, what about 21? If you're worrying about the difference between 21 and 22, you're probably focusing on the wrong part of the story, or between 3 and 3.1 and 2.9, right? But basically what we're saying in terms of strength of evidence, right? A Bayes factor of 1 to 3, they say not even, not worth more than a bare mention, right? 105 falls in probably not even worth more than a bare mention, okay? If we get a Bayes factor of 3 to 20, starting to classify this as positive evidence. 20 to 150, strong. Bayes factor greater than 150, very strong, right? But again, remember that all of these are Bayes factors based on a best case scenario. That's not realistic. That's probably never the case, right? So even that 0.05 level of Bayes factor 2.46 is probably, that's the upper bound. That's the most, based on the data, the highest Bayes factor that we could expect from this. So again, taking that into consideration as we're trying to judge or draw inferences from studies. Questions about this? All right. Okay. Yeah, if you have p-values that are greater than 0.50, like this is the thing. Unless I explicitly make you, don't worry about calculating S values and Bayes factor values for tests with p-values greater than 0.05. Because you already know that we don't have evidence for it to begin with. So calculating something that tells us that it's even more tenuous is probably not helpful. As soon as you get p-values that are above 0.5, things kind of flip around and things get weird. So just be aware of that. All right. So this is just some examples for different odds. If you do stuff with logistic models and categorical outcomes, a lot of us don't. Amanda, I know that you will, and sort of jury decision making and things like a lot of this is sort of yes, no jury decision making. And so psych and law tends to work more with some logistic models and things like that. Chris's students, sort of public health, you get into sort of risk models and things like that, like is this thing present or absent, more of that type of thing. we'll get to this at the end of next semester, talking about how logistic models are chronically underused. They're actually quite flexible and quite good. But this is just go through and take a look and thinking about sort of trying to take sort of some of these odds and tie them into things that are kind of more easy to think about, right? Like rolling a dice that's rolling 2 dice that's less than 5. Is that right? Yeah. So just go through and take a look at that. Is trying to get some or no, 1 dice. Yeah, 1 dice. So yeah, because so again, the likelihood of me rolling a value with a single dice that's 3 or less is even odds. I get 1, 2, 3. It could be 4, 5, 6, even odds, right? Here for 2 different cards, poker stuff, just to kind of see gauge for likelihood of things popping up. Okay. This is just going back to when we're talking about Bayes factors, this idea of posterior probability, prior probabilities, posterior probability, prior probabilities. This is probability of an event based on existing knowledge. So before I even do anything, what's the prior probability of the alternate relative to the null? Posterior probability, this is sort of our assessment of the probability of an event after data have been collected. Okay. Again, going back to that example that we worked on previously, right? This idea of this is from the Cohen paper, the probability of schizophrenia out there in the population, we'll say it's 2%. So the probability of the alternate is 0.02. We've got a screening measure where we have a probability of a positive test given a positive case is 0.95. Probability of negative tests given a non-case is 0.97, and we're pretty excited about that, right? We're saying, okay, hey, we've got a pretty good test. This is doing good. But again, if we start to flip these around, right, and we want to know the probability of a normal case given a positive test, right? Now all of a sudden we have to have prior probabilities and things like that going through. And as we walk through this example, it starts to get pretty poor, right? If my prior is 0.02, right? If I say the likelihood of my alternate hypothesis relative to my null hypothesis isn't 50-50, it's 2% or what was it? 2 out of 100, right? Likelihood balance there relative to 50-50. You get a probability of a non-case or the null probability of null given a positive test. So the probability of our null, probability of the null hypothesis given a positive test statistic is actually quite high and quite likely, right? But if we go through and we say it's even Steven, my prior probability is 50-50, which is Matt, where are we assuming this case?
Sorry, I'm just trying to write down notes, so I don't have the slide, so
Oh,
I'm lost.
you don't have this slide? Okay, so I'll go through post this slide, so don't worry about this. So just conceptually sort of understanding sort of what's happening here. Okay, so with so to this case, we've got a low base rate situation, right? We don't have 50-50 odds. We've got sort of much lower than that. Okay, here we got a 50-50 case. If we look at the probability of a probability of the null given a positive test, here we get 0.031. Okay, what's someone tell me the relation here, the difference between these two?
Prior example, the probability is much higher.
Yeah, right. Sort of with this one, right? So if schizophrenia afflicts half of the people in the country, how likely is it that I'm going to have a normal person have a positive test? That happen very often? No, it doesn't, right? That's really low. What if I jack around that prior though and make that prior 2% instead of 50-50? How likely is it now that I get a normal case with a positive test? A lot, over 50%, right? And so just thinking about when really trying to hit home with this idea of with these Bayes factor bounds, like it really, really is like the best case scenario out there, right? This is what our Bayes factor bound is assuming this situation, right? This is more like probably what's going on out there in the universe, right? The likelihood of my conditional indirect effect being something that's reasonably different than 0 probably isn't a 50-50. It's probably not a coin flip, right? It's probably something that's sort of more along those lines, right? And so when we do that, just looking at the impact that this has on this on our estimates with Bayes, so that those priors make a big impact on this. This is what we're assuming with our Bayes factor bound. This is probably closer to reality, and so there's a big difference between those two. Okay, so just recognizing that even though we're recommending providing these Bayes factors and interpreting them, always making sure the emphasis is that this is under a best case scenario with even odds for the alternative relative to the null, which probably isn't a case that ever actually holds in real life. All right, sorry about not having this in there and making you scribble furiously. If someone would shoot me an email or something like that real quick to remind me to plug that back in there, otherwise I'll forget about it. Okay. All right. Okay, questions about S values, Bayes factor, things along these lines. What we're going to do is we're going to start incorporating these in our interpretations, mostly just to help us get a more sort of maybe intuitive sense for the likelihood or the extent to which our data are inconsistent with our null hypotheses. All right, so we're going to jump back into our single sample t-test, right? I've been talking a lot about assumptions of our single sample t's, or talking a lot about assumptions of our statistical models. Some assumptions for a single sample t. Teresa, can you tell me when do we use a single sample t? Okay, yeah. So yeah, we need to use the sample variance, right? Because we don't have an estimate of the population variance, right? Good. Remember, single sample t is when I have a sample, just one sample, and I want it to compare it to some population value, right? But I don't know the population variance. I know the mean, population mean, or some reference value that I want to compare to, but I don't know the population variance. If I don't know the population variance, now we're off of Z statistics, and now we're working with T statistics. Yeah.
So this might be an example, like if you had a control group and and you wouldn't even really have a whole other group, but you just have control groups, and maybe you wouldn't really know. I'm just trying to figure out when would this be like in real life?
Yeah. Not often. When will this be in real life? We don't use this a whole lot, right? Because we're generally often trying to compare two groups. We rarely have a population mean value that we do know that we're trying to compare against. But let's say if, does that remind me of what sort of your area of stuff is? What's that? Social identity, right? So if you had some measure in that, in general, sort of the population sort of gens to, or sort of based on not population values, but like maybe large scale sort of development data that sort of people, let's even say just college undergraduates, tend to have about this value. You've got a new sort of interesting population that you're interested in looking at identity. People haven't actually sort of looked at this group of individuals before. What you might do is say, okay, here is a reasonable sort of sample of this new population I'm interested in. I'm thinking they're going to score lower on this identity measure than sort of what we would have in terms of sort of general people. And that's sort of important for my hypothesis that, yeah, this identity stuff is particularly salient for this specific subpopulation. Then I could see using maybe an independent, a single sample T, right? Because I've got just my sample and I want to compare it to some known benchmark. Okay. Does that kind of make some sense? Okay. Yeah, doesn't happen a whole lot, but we'll play around with this in this next assignment. You get an opportunity. Okay, so assumptions for our single sample t. We're assuming that our outcome variable is continuous or some ordinal scale with 5 or more values. We start to treat our ordinal data as though it was continuous. Fortunately, for our means-based analyses, it works out okay for the most part. Technically, looking at continuous outcomes, we often end up working with those with count variables and stuff like that, which actually probably isn't the best way to do it, but it still holds up. Our research methods research says it holds up okay with this. Okay, we're assuming that our observations are independent. What does this mean? What do you think?
But you're not taking other studies into.
Kind of, okay. So we're talking about, so I've gone through and gathered a sample, okay? Elizabeth, what am I wanting in terms of, if I say I want these observations to be independent, what am I saying there? Yeah, you want to add to that, Basha? Not influencing one another, okay? So if I go through and I include you all in my sample of whatever, I want Amanda, your scores to be different than Elizabeth's score, different than Teresa's scores to be different than Sam's scores. I don't want your scores to influence one another. If we do that, we've got a complex data structure. So for, let's say, Emily, if I'm looking at behavior problems in a classroom, and I'm sort of collecting everybody from the same classroom, and also have another group of students from a different classroom, there's dependencies because spatial dependence going on with these groups versus potentially any 2 observations within this class are going to be probably more similar than any observations across classrooms. And so we have a dependence if we've got that type of metadata, got some problems. So our t-tests are going to assume that our observations are dependent. And then what we're assuming here in terms of our distribution, we're assuming that the distribution of sample means for the population is normal. Okay. Someone tell me, under what condition does the distribution of sample means start to approach normality very quickly? What do you think?
When the underlying construct is normally distributed.
Yep, when the underlying distribution is normal, and when else?
When you have sample size or samples, you'll have at least 30 samples of same size samples.
Okay.
I can't speak to that.
Yeah. So yeah, you're keying in on this.
Yeah.
I push it off at 30, right? Because there's nothing magical about 30, right? We've got that sort of that curve going on there. But so really what we should be saying is that as long as as our sample sizes start to sort of get larger, sample sizes getting increasingly large, that distribution of sample means will approach normality real quickly. 30 is kind of a rule of thumb, but it doesn't matter. Like, so if I have a sample with 31 people and a sample with 29, it doesn't mean that one's bad or the other is good. It means functionally the same thing, right? So you're exactly correct. That's what we use, but just want to make sure that we're being flexible with that. Okay. So even if I've got some crazy looking data, okay, and it's not super well distributed, right? Have I violated my assumption of my test? No, why haven't I?
Well,
Yeah, right. Basically what we're saying is my normality assumption applies to the distribution of sample means, not the observed data. So the observed data can look kind of wacky and crazy. Now, if I've got a small sample, and I got extreme values that are dragging my mean around or exploding my variance, then that's going to be problematic, right? But I can have data that has skew, kurtosis, is kind of flat looking. Maybe it's kind of all jagged because when I have small samples, it's going to look weird a lot, right? I don't worry about that necessarily because of the assumption of my test is about the distribution of sample means, not the distribution of scores, okay? So I can have scores in my sample that look kind of funky, but as long as if either sort of the thing that I'm sampling from, I can be reasonably confident kind of approximates a normal distribution, or I've got reasonably large sample sizes or cell sizes, I can assume that the distribution of sample means is going to be normal, and that's all I care about for my team. You see people get blown out of proportion back. Well, your data is not perfectly normal, or I have a skew value that's statistically significant, and so I have to do some non-parametric transform. That's a misunderstanding of what we're trying to do. Now, if we've got weird stuff that sort of really kind of trails out, if I've violated, I don't have a true continuous scale, I've got a count variable, and we've got people who are way out of bounds, then maybe, yeah, I need to go through and start sort of thinking about working on it with some transforms or something along those lines. But our assumption of the test involves the distribution of samples, not the distribution of scores. It's an important, this is an important consideration, an important thing that allows us to apply these tests when otherwise we would rarely be able to, because data rarely behave the way we would like to and are nice and normal, particularly for small samples. Questions on any of our assumptions here? All right. Informal assumptions. We're assuming that our data don't contain extreme values. Let's remove outliers from our vocabulary, because that's sort of implying things. So the data don't constrain extreme values. This is to some extent is based on a sample size. If I've got a sample of 300 people and I've got someone hanging out there on the edge, I'm probably not too concerned about that person, because one person, unless I'm looking at income, and I manage to grab Bill Gates in here or something like that and just, pull it way the hell out to that one end, I'm probably not too concerned about that. For the types of things that we study, or sometimes to get something that's going to be that much of an outlier that's going to drag stuff out in a big sample. When we're working with small experimental studies, though, right, we got maybe cells of 20 people, 30 people, maybe. If we've got someone who's like way pulling the stuff way out, we might start to be concerned. But we're still going to go through and evaluate our data, see what the shape looks like, see what our data is looking like before we jump in the middle of things, just to make sure that we're not missing something that's going to have an inordinate impact on our results. Questions? All right. So our auxiliary hypotheses, again, this is all the stuff going on in the background that we conveniently ignore. But if we're going to take our stuff literally and say, oh, yes, I haven't violated it, these are all our ancillary hypotheses. We're assuming the sample is representative, that it's random, I have no violation of assumptions, that I generated my hypotheses prior to sort of collecting my data, my model is correctly specified, I've included relevant variables, my measures are valid, my measurements are collected without error. Like, this is not anything that ever happens, probably. And so what we've done is sort of created a blind spot where we pretend that's not there. Very much is there, and needs to be something that we're considering when we're trying to draw inferences from our tests. Okay. And all of these things, as we start to click down and sort of accumulate checks here, it starts to make us more and more maybe modest in terms of our interpretations of what we've got. Again, we're not saying that it's all crap and garbage, because if that's no one would ever do research, we can't ever do this. But we're still doing it. We're just trying to be acknowledging, recognizing that these are things going on in the background, and sort of trying to think carefully about this, how this impacts the results that we get and the types of inferences that we're drawing. Questions? All right, so we're going to do an example in SPSS. People have this single sample t-test sort of set pulled up. Pull that up and get that loaded if you haven't already. So what we've got here is a set of scores from the IAP 32. This is measured in terms of assess domains of interpersonal difficulty. We got scores ranging from 0 to 128, with mean equal to 25 and a representative validation sample of 800 adults. I think this is from the manual. I think I pulled this, so this is real life. Validation sample, 50% women, 77.7%, about a little over 3/4 white non-Hispanic. Age range 18 to 72. Education, about half, little over half, less than 12 years. So we've got sort of people with high school degrees or less making up half of the sample. Oh, yeah, 13 to 15 years of education, about a quarter, and then about 70% with more than 16 years. So kind of just giving the population from which this was drawn, trying to give you some parameters, okay? Researchers are interested in the effects of stress exposure on global interpersonal functioning. Response to the IP32 obtained from university undergraduates reporting the stress associated with exposure to prior trauma, okay? And so our sample that we pulled from is again about 3/4 women, about 80% white non-Hispanic, but has a mean age of 20.5, standard deviation of 4.6. Okay. So what we want to do is we want to state the null hypotheses, state the null and alternative hypotheses. We want to calculate a confidence interval for the point estimate of interpersonal difficulties in our sample. We want to provide an index of the absolute magnitude of the difference sample relative to the normative population. We're going to conduct hypothesis tests. We're going to report and interpret our S value, going to report and interpret our Bayes factor, and then we're going to tie everything and summarize everything up and say this is what we can say based on this data. So what we're going to do is we're going to walk through running single sample t-tests with this. This is what we'll do. I'll pull this up on the screen here in a moment and go through. And so with SPSS, show of hands, who's familiar, used SPSS before? Basha, you haven't ish. Not every Josiah. So Basha, what statistical programs have you used previous? What's up? Look at you, fancy. You think you're better than me? Okay. All right. What about you, Josiah?
Excel.
Excel? Okay. All right.
Not really.
Okay, cool. SPSS, people gripe about SPSS a lot. I will, but for in terms of this type of stuff, it's a slick system, right? The major drawbacks is they charge you sort of every year for something that they are not sort of making sort of probably big adjustments to and things along those lines, right? But it will do sort of everything. It's a nice slick sort of interface, and so it ends up being a nice way to go through, pull down menus and find the types of analyses you're doing. But for this class, what I'm going to get you, encourage you to do, will force you to do, and I'm not encouraging you to do it because you don't have a choice. I'm going to have you start to sort of run things through a syntax file. Who's run syntax files with SPSS before? Okay, a couple of people. It's easy peasy. The syntax with SPSS is not intuitive, right? But what we can do is we can paste our commands into a syntax file. Then you just save that syntax file. And once you start to get comfortable with this, then it's just sort of changing variables out because you're going to be doing the same stuff over and over again. So right here, we just have a syntax syntax for our one sample t-test. You don't have to know this, write this down. SPSS will drop this into your syntax file for you, and then you just save that and you're good to go, okay? But let's go through and minimize this and bring up SPSS, okay? So here's our data set. People have this open and working with stuff? Okay. So what we've got here, and this is sort of to simulate sort of the situations you'll find. We've got a set with a lot of different variables. What variables am I interested in gathering right off, or which of these variables am I actually interested in? Total scores, exactly. So right here. Okay, I'm going to tell you this right now. When you give you data sets to work with, just because there's variables in the data set doesn't mean you have to use the variables for anything. Make sure you're reading problems to know which variables are relevant and which ones aren't. In SPSS, if I go down here, we've got data view. If I click over to variable view, it tells me what, if I've done a good job of labeling my variables, what all the variables are, so to help me kind of understand what's happening with this stuff, okay? So I'm going to switch back over to data view. And so with our screening, what we're going to do is we're going to start out with the screening. First thing I always want to do with the screening is I want to see, check for missing data, viability of scores, so that I don't jump into something headlong and start saying, okay, so what's happening? I get halfway through and then recognize I have to work backwards. Okay. So first thing I'm going to do is I'm going to take a look for missing data. Okay. So in SPSS, what I'm going to do is if you go through, you highlight that column, and you could go data. Where's sort? Sort's in here. So I'm going to sort cases. Okay. And hit that. And I'm going to say, I want to sort by, let's say ID number, and I hit OK. And it's going to sort by ID number, but that's kind of takes a long time. What I'm going to do instead is I'm going to go over here, click on IIP total. I'm going to right click, and then I'm just going to sit sort ascending, and it's just going to sort it all. Right? It's just a shortcut. Okay. What are we seeing here, Emily, just right off the bat in terms of missing values?
For participants, a lot of participants without any questions.
Yep. So I've got a lot of folks who we don't have any of these IIP scores for, right? Okay. 70 of them. If I don't have data, can I use those cases? Nope, I sure can't. So what I'm going to do, always, 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 okay. First rule of analyses data management, have a file that has your data, that's your original data, save that, and then leave that the hell alone, okay? What you don't want to do is go jacking around a data set and delete a bunch of stuff. If it's the original data, if that's the only copy that you have, and now all of a sudden you're pretty sad when you need to go back through and recover that stuff. So always have your original data. And what I do is I usually go through and we'll open up a file and just save it as a working set. So whatever the data is same is working set. Or if it's something I don't care about, I'll just name it scrap or something like that, right? Always make sure that you have your original data that you can sort of go through and make copies of, but not something that you're actively working on, so that you can always know, hey, this is where we started from. Okay. So what I'm going to do first is I'm going to go through, file, save as, and I'm just going to call this scrap because I don't care about it. It's a scrap file. Okay. Now what I'm going to do is I'm going to take those, I'm going to mark down, I'm going to say, okay, I've got 70 cases that had no values for the IIP total. I'm going to highlight those and I'm just going to right click and hit clear. All right. So now I'm down to just data variables with full data. Okay. How are we feeling about that? Yeah. What's that? You could do that. You could just leave all those alone and just sort of go with that. The problem is we start to get into data that has multiple variables in it. If I go through and I have cases with some variables and not the others, as I go through and start to screen, I'll be screening different subsets of the sample. This is just what I like to do because then I'm just working with a clean set with complete information, and I don't have to worry about sort of whether or not I'm sort of running distributions in this sample of 73 and then getting distributions for another one in a sample of 64 and sort of working with this stuff. Okay. Other questions? All right. So first thing we're going to do then, so we got rid of, so we marked down, we've got missing data, right? We got 70 cases with missing scores. Make sure we're marking that down. What I want to do now is I want to go through and I want to take a look at my distribution of my outcome. Okay. So what I'm going to do is I'm going to go to analyze. I'm going to go to descriptive statistics. And then I'm going to go down to descriptives. And I'm going to look at my IIP total because that's the only thing I'm interested in right now, right? So put my IIP total here. And then what I'm going to do is I'm going to go to options. I'm going to ask for skew and kurtosis. I'm going to hit continue. And then on this box down here that says save standardized values as variables, I'm going to click that. Okay. And then what I'm going to do is I'm going to go ahead and I'm going to hit paste. All right, when I hit paste, that's going to bring up my syntax file. Get rid of that data set active. I don't care about that. This is the command for this descriptives that I'm going to run. Okay. I'm going to want you to get into practice to keeping these syntax files up with what you want it with the analyses that you're doing. What this lets CJ and I do is if you're way off base in terms of an assignment, sure your values aren't matching up. This gives us a record of what you've done. So I should be able to go through and take your syntax file and run that on the data set that you've given us, and everything should come out. That way we can go through and figure out sort of where you made your mistake, help you along with this stuff. Okay. Nice thing with these syntax files, if anything that you start with an asterisk is going to be a comment. Okay. So I can say, oops. Looking at distribution. Okay. That's not something that's going to come through and it's going to run. It's just telling me, help me keep track of what I did and where things are going. Trust me, we're going to be doing the same types of screening over and over and over and over again. Probably what you're going to have eventually is it's going to be the same set of commands you're running on everything, right? You just have a syntax file that says single sample T screening. You just pull that up, change your variables around, and then you're going to be good to go. Okay. It's a lot more efficient than working through all the pull down menus and things along those lines. Okay. So what I've got is I've got this command. I'm going to highlight it, hit my green run button, and it's going to come up here. Okay. Now this is kind of small to see on the screen, but someone help me walk through this. What are we seeing here, Sam, in terms of this output? Why is that?
You have a really high value.
Yeah, what's happening there?
It is. You got a maximum value of 999.
Okay. Okay. What's the max value of this IIP variable?
128.
It was 128, right? So is 999 a viable score on that? No, right? So either two things happened here. Either one, if I go through and we go back and take a look at my, go through, sort this, right? Go all the way down to the bottom. So I've got a value of 99, that's in bounds. Two things happened. Either someone entered this and they hit an extra 9, or probably the more likely situation is, again, I've said this before, what I do in a lot of my sets when I'm having people enter stuff, if we've got a missing value, I have them enter 999 because 999 is rarely an actual real value for anything. That way, I actually have a value in there that tells me that, hey, this is a missing value, as opposed to just a blank space. Because if it's a blank space, I don't know if it's really missing or if someone forgot to enter it or what happened, right? Problem is that sometimes I will create data sets with 999s in them, but not tell SPSS that 999 means missing data, right? So what I can do, if I go to my variable view, click that and see this missing, what I can do is I can go for IIP total. I can move over and click this and say discrete missing values, 999, and hit OK. And now go back. And now if I go through and rerun this command right here, we'll see what SPSS has done is it's no longer recognizing, it's just identifying that as a missing value, right? And so now we have descriptive statistics that are in line with what we would expect. Okay, so Emily, what else are we seeing? So we've got rid of that 999, and so I would want to go through and mark on my, because I'm screening this, keeping track of the participant number that we had, that 999 value, because that's something I want to go back through and figure out what's going on. If it was really missing or a miskey, whatever. So I document that, take care of that. But what am I seeing now, Emily, here with my descriptive statistics? Yeah, we got a big standard deviation. What's our sample size look like? 334. Okay, cool. So even if this happened to be a really ugly distribution, am I worried about the distribution of sample means? No, I'm not, right? This is a really large sample. Distribution of sample means for a sample this size, going to be normal real fast, right? So I'm happy about that, right? So I'm not worried about my distributional assumptions. But if I go through and I take a look at my skew and kurtosis values, right? Are those skew and kurtosis values anything that I'm going to be concerned about or worried about?
I can't remember what.
Yeah. So what do we?
Yes.
Okay. What do we talk about or about these values for skew and kurtosis? When do we start saying like, that's starting to get something that's maybe having a noticeable deviation from normality? You remember? It's generally 2, right? So if I have skew or kurtosis greater than 2 is kind of a loose rule of thumb to back, I would say, I would talk about it as deviation, notable deviations from normality, right? But again, you want to be very careful about how do we assume, is it assumption of our test that our observed data are normal? Nope, it's not, right? And this is what happens. And you'll see this when you're reading papers or sort of down the road when you're reviewing stuff. People will say, we had significant skew and therefore did a bunch of crazy ass stuff to this. It's not necessary because it doesn't matter, right? And if I were to go through and let me see if SPSS will even do it. Maybe they don't let you do this anymore, which would be awesome. Yeah. Sometimes what people will do is they'll run, start to generate p-values for this value of skew and kurtosis, okay? Let's say I ran a p-value on this skew or kurtosis, and I got a p less than 0.001 for my kurtosis value of negative 0.611. What does that mean? What does any hypothesis test ever mean? What do you think, Josiah?
That is random or not?
Not random, that it's the skew is not likely not what?
Possible.
Under the null, and what's our null value? 0, right? I can attach a p-value to that, and that p-value, particularly with the sample of 334, is probably going to tell me that it's unlikely that this value is coming from a distribution with a skew of equal to 0. Do I care if skew is equal to 0? No, I don't care. Like, so I could care less if it's significant or not. And this is the problem with sort of attaching significance to things. It just means that something's not 0. But rarely do I ever care if something is exactly 0, right? But if I don't know and I'm not careful, what I do is I see significant skew. And now I've gone through and done a bunch of stuff that complicates my analyses that's not necessary and impacts interpretation because I've got a skew of negative 0.61, which is perfectly fine. And there's nothing wrong with that with these data, right? So again, sometimes I'll be reviewing a paper, they're like, well, because we had significant skew and kurtosis, we went through and ran it through 7 different transforms that now it's hard to know what we're actually looking at, right? When it wasn't necessary in the first place, okay? So always be careful. Recognize just because something says it's statistically significant, that just means something's likely not 0, okay? Whether that's important or not, that's a completely different situation, okay? So SPSS isn't even providing it here. Sometimes programs will. Here we've got values of skew of 1.87, so slight positive skew, some negative kurtosis. What shape is negative kurtosis? What do you think, Basha? You're sort of running through it in your head.
The curve is like to the right.
Okay, so that's skew.
Oh wait.
That's skew. What about kurtosis? What's negative kurtosis?
Not like the steeper or flatter. So
Okay. That's going to be positive kurtosis, leptokurtic, which is
so
the other one, right? So negative kurtosis. So it's kind of boxy, heavy shoulders, just kind of rounded, domed type of thing, right? Okay, so we've got indices of skew and kurtosis. And so this gives us a nice actual sort of point estimate of a metric that tells us that we have some negative kurtosis, some positive skew, but nothing that's even close to anything that we would be concerned about here. So we're feeling probably all right with this, but what we still want to do is we still want to go through and run this distribution and sort of look at pictorially what our data look like. Okay, so what we're going to do is we're going to go down through, mark kind of what we've got here. I'm going to go back over. We're not here yet, but with this, remember that with my descriptives, I asked it to save standardized scores, and it's done that a couple of different times. I'm going to get rid of those just because, I'm going to get rid of those. And then this 999 variable, I'm going to get rid of that. I'm going to mark to say 414 is either a miskey or having a missing value. Either way, it's not plausible. So we're going to get rid of that. Okay. And now I'm going to rerun my descriptives here. And it's just telling me, okay, so now I've got my z-scores and stuff like that. But what I'm going to do now, I want to go through and get some graphs. I'm going to give you a shortcut for this in the next example, but for right now, what we're going to do is we're going to go to graphs. We're going to chart builder. Okay. And it'll tell you, complain about something. You say, okay. Okay. What we want first is we just want to get a histogram. Okay. So down here in gallery, we're going to choose histogram. We'll grab this first guy and pull it up here. We can go down, find our IIP score, drag that in here, and then I'm just going to hit paste. Okay. And here's my big old crazy syntax for this graph. I'm just going to go through and run it. It's going to give me a nice little graph of my histogram of my scores. Okay. Sam, what are you seeing? Like, how would you describe this histogram? Yeah.
It's like a little messy, but it's.
Yeah. Okay. So this is where you're going to get good, because I'm going to have you describing a lot of different graphs, right? Things we want to talk about, sort of the symmetry of a graph, sort of normality of graph, sort of multimodal stuff, sort of dispersion, tails and things along these lines, right? And so here I would say, so that these data, and so if I'm looking at this, I can see, so the little bit of skew, right? Because we got kind of this headed off over here, but is this anything we're worried about? No. We saw some negative kurtosis. I can kind of see we don't really have tails to this. It's kind of a little bit boxy, right? But I don't know. I might call this data, so this histogram is relatively symmetrical. With, and then sort of maybe would say with one value extending sort of separated from the higher end of the distribution, right? To just kind of say, this is kind of what it looks like, right? One thing you'll see in the screening examples that I gave you, will sometimes describe data as unremarkable. Use that sparingly, okay? Because what I get is assignments where everything's unremarkable. I'm like, nope, nice try. Tell me what you're actually saying, right? Use your words, describe kind of what's going on with these data so I can get a picture in my head about sort of what's actually going on with your data. But based on this, so we described this as somewhat symmetrical. You know, I mean, I wouldn't worry about multimodal type of thing. Is the thing with histograms is depending on how you bin this, it's going to make the graph look different. In SPSS, you're just going to go through and use the defaults, but I wouldn't get too worried about multimodal sort of anything here unless it's really prominent, because if I were to change your binning, it's going to switch things around anyway. Okay. But based on this histogram, is there anything that you're concerned about in terms of these data as far as violations or sort of things that should cause you concern? Looking pretty good. Okay. Other thing I'm going to have you do is I'm going to have you go back up, go to graphs, chart builder. This time I'm going to have you go down, select box plot. Okay. For just our single sample, we're going to take this one box plot, drop it up here. You got our IAP totals. It just kept that going. I'm going to go through and paste this. The nice thing about our box plot, this is different. These are median-based statistics, right? As you've gone through and described already. But the thing about the box plot is the same no matter what program you're running, no matter what the data. The midline is the median. The bounds of your box are the first and your third quartile. Your whiskers are calculated the same. Now, different programs will do different things for values falling outside of your the upper and lower bound of your whisker. But it's unlike your histogram, which I can start to change the shape of it based on how I'm binning those data. Your box plot's always going to be the same. Okay. So we're going to go through and run that box plot. I don't know. What do you think, Matt? How do you like that box plot? It looks pretty box plotty, right? What words would you use to describe that?
Positively skewed, but I'm not 100% sure I'm confident on that.
This is a plot I would say box plot. You could reasonably say box plot was unremarkable. Right? There's like nothing too much going on. You've got the midline that's falling about sort of down the middle of the center of in between your first and your third quartiles. You got maybe this upper whisker kind of creeping out a little bit farther than the lower bound. There's sort of not much. You might say slight positive skew evidence in the box plot, but sort of nothing else, nothing really too much going on here. Okay. So based on our run of our assumptions, our graphical interface, any concerns about what we've got going on with these data? Okay, cool. Last thing we're going to do here is I'm going to go through and I'm going to look at these z-scores. Okay. Someone tell me what these z-scores represent. Amanda, do you know? What's that? The z-scores here at the end. The z-score of my IIP total. So what do these represent? Yeah, perfect. In standard deviation units, right? You look at that, that is just about 2 standard deviations underneath. Z-scores are fantastic, just like any other standardized score. It's just giving me a number in terms of standard deviation units. What I want to do is I'm interested in sort of, do I have extreme scores? I already know based on the plot that I don't have anything that's too concerning, but just to be thorough, what I'm going to do is I'm going to go through, because in my descriptives, when I asked it to save standardized scores, it's just creating z-scores for all of my values centered on the mean. So if I go through and I go to analyze descriptives and take out IIP, unclick standardized values because I don't need to look at z-scores of z-scores. Move my z-scores over here. Okay. And then I'm just going to go through and uncheck skew and kurtosis and continue with that because I don't need. Is my skew and kurtosis, my z-score is going to be any different than the skew and kurtosis, my observed values? No, it's going to be the exact same, right? So what I'm going to do is I'm just going to paste that in. And so now go through, take a look at my z-scores here. All right. So, Teresa, what am I seeing with my z-scores here? What is this telling me? Is the mean of my z-scores negative? What's the mean of my z-scores? Okay, yours is maybe negative because you might have, and this, I'm glad you did this. Always be careful when you're calculating those z-scores that you've calculated on this, that you're looking at the set that you, because if I go through and remember I had 999 in there, if I calculate a z-score for that with that in there, that's going to be a massive z-score. And then if I don't delete that, and then I go through and run it, I'm still going to get the z-scores that were calculated are z-scores that were calculated based on having that value in there. And so always make sure before you look at your z-scores that it's that those z-scores are run on the final sample that you want to go through and take a look at. Okay, so here are z-scores, and so you know how you see this? You take a look at your mean of your z-score. If your z-score isn't zeros across the board, it means that something's gone wrong. Okay, because by definition, mean of z-scores is 0, standard deviation is 1. If those two things aren't 0 and 1, you know that I've made a mistake somewhere, and it's probably that I've got, so I calculated these scores with cases that aren't no longer in the set. And so I need to go through, delete them and sort of rerun it. Okay. But if I'm looking at my min and my max, right? Like this is a nice way to metric extreme scores and be very exact in terms of how far out are these things. So Teresa, what might I conclude based on my minimum and my maximum z-scores here? So my minimum is about -2. My positive is about 3. Okay. If I have a score that's 3 standard deviations from the mean, is that a big score? That's a pretty big score, right? Am I concerned about that for these data? No, why not, Basha?
So we're gonna do distribution of samples.
Okay.
At that, it all goes to normal.
Well, that's true. So I'm interested in the distribution of sample means, but sometimes we can have, even though we're sort of relying on distribution of sample means, and that will be normal, sometimes we can start to have extreme values that start to drag my mean around. Okay. Is this, we got a high score, 3 standard deviations above the mean, right? Is this likely to have an impact on our data? Why not? When you want to help her out?
How big our sample size is?
Yeah, our sample's huge. We got a sample of 334, right? So even though I do have a large value in this distribution, that large value is not going to be something that's big enough to go. Now, if this was a z-score of 15 or something like that, then I would clearly have something that's probably a mistake, right? And so, yeah, if I were to calculate the z-score for that 999, that would be sort of way the hell out there, and then that would obviously be a problem. But here, it's not too bad. So we usually sort of what we do is we can set kind of threshold for what I'm going to call an extreme value or something along those lines. And oftentimes we tie that into p-values for that distribution, right? So like 3.29 or 3.3 is associated with a z-score of p equals 0.001, right? And so we would say, well, if it's beyond, that's sort of an extreme value because it was be associated with a low probability value. We can go through and do that. What I would prefer to go through is go through and take a look at this within the context of your distribution, okay? Amanda, where's that z-score that's sort of right at 3? Which case is that in the distribution here? Yeah, well, I know exactly which one it is. It's that joker right there, right? That's what it is. It's just a large value. Is this value going to pull the mean off of any of this stuff? No, it's not going to be. So we would say maybe that we have one value associated with a z-score. And then if I go back through and I take a look at my data, okay. So I might say case 428 has an IAP score of total of 99, which is associated with a z value of 2.94. This value falls sort of beyond is separated from the upper end of the distribution in the histogram. However, it's not likely to impact much of anything. Okay. Yeah.
So
Uh-huh.
I understand if the z-score is extreme. Look at our graph and see that
Yeah, and so this is where we start to get into some of the nuance and be able to take in multiple pieces of information to make a determination. Z-scores are nice because it gives us a value that we can say, this is telling me exactly how extreme this value is, right? But in combination with the histogram, what I can, so the sample size, I can say, yeah, we've got a high value that's falling a little bit away from the upper end of the distribution. This is the Z value. It's associated, it's about 3 standard deviations above the mean. This is the actual value on the measure that sort of resulted in that Z score. But given the size of the data, it's not a point of concern. Okay. And so again, using that Z score, again, it's just giving us a metric because if, let's say Emily says, oh yeah, I had an outlying value that stood away from the rest of the distribution. I don't know what that means, right? That could be associated with the Z value of 1. It's just I have a really tight distribution and then this someone's just hanging out here, or it could be someone way, way out there, right? That Z score is a nice way. It just gives you a metric. Say, oh, this is about how far it was. Communicates information, which is always what we should be thinking about in terms of statistical writing is sort of, am I communicating interpretable information to somebody else, right? So if you go through and take a look at the in-class example of the single sample T. Okay. So what we'll see, what I want you to do before, I used to let people psych jazz and just go through and write up their own screening summary. That was a mess because people had all sorts of, this is the format I want you to follow, right? So here with the screening, we start with missing values. We say missing IIP scores in 70 cases, right? We're just saying, hey, we went through initial stuff. We're missing a bunch of data for this sample. Accuracy and plausibility. We have an invalid score of X equals 999 for case number 414. And then we just say cases with missing and implausible values removed results in a set of 334. Okay. Then we say univariate distributions, skew and kurtosis, fail to indicate problematic deviations from normality, right? So we're looking good there. We're saying histogram is symmetrical with one case falling slightly away from the continuous distribution. So we're noting that this is sort of falling above. Univariate outliers, fail to provide strong evidence of univariate outliers. All Z's are less than an absolute value of 2.94. Yeah.
Is that sheet?
Yep, it's all in those handouts. So make sure you have those handouts pulled up. So otherwise you're gonna be lost. What's that?
What is it called?
It's your screening summary in there.
Okay, thank you.
Okay. Then we've got sort of univariate outliers. Now there's strong evidence there. And then recommendations, we say substantial missingness in over 70% of the cases, right? Yeah.
The screening said that it's in the same place.
Oh, nuts. Okay.
I thought you said it no.
Okay, I'll get a different one. I'll get it fixed. I'll get it up to you over break and then you go through, take a look at that. Okay, cool. Says I need to do a better job of labeling sort of what I'm sort of up to with this stuff. So sorry about that. Yeah, we'll get those sort of posted up and make sure we got the right ones. Okay, but going through talking about little evidence of outliers of problematic violations of normality, and then just kind of bringing it all together here at the bottom, say missingness in these data is concerning given potential for systematic biases in subsequent analyses, right? So the biggest thing we're concerned about in this screening is the fact that we're missing a bunch of scores. However, assuming some methodological justification for missing values in this set, this was a set where we didn't introduce this measure until halfway through the thing. So I know exactly why all those data were missing is because those cases didn't have values. Cool. Accounted for that. That's no longer a concern. Recommend proceeding with our means-based analyses. There's looking pretty good. Nothing really going on. We're good to go here. Right. So this was a lot. Screening always takes 4 times as much time as the actual analyses, but the the single sample T is a good sort of way to get our feet wet with stuff, right? Questions on any of this? Okay, let's go through, take a break, and come back at say about 5 till, and we'll jump back into the actual work of like actually screening thing or actually running our test. All right, so those handouts, so the new ones that I uploaded there, the electronic files, that'll give you an example, or sort of the example that I was just reading through with those. The general screening is going to follow for our means-based tests, whether we're working on ANOVAs, whether we're working on t-tests, just kind of giving you an overall description about sort of what we're looking for in each one of these things. So use this. I don't give you templates, really. I want you to sort of think about sort of your own stuff and how to go through and put it together. But for this, in terms of organization, a way to sort of try and put things together and communicate to me in a way that makes sense to me too, and CJ, so we can go through and do this. This will be kind of the format. So you'll see in that in the electronic file that I uploaded to Wild Courses, you'll see we've got talking about missing data, and we talk about plausibility of scores, and we say, okay, based on that, we've gone through, take a couple of, or I guess 71 people out, talking about sort of this is the my reduced set that I'm working with, talking about our distribution, and then after that, talking about some outliers or extreme values, get into some recommendations, right? So in the recommendations section, this is where you just get to, this is where you get to play statistical consultant, where you're saying, hey, this is what you got going on in these data, talking about how this may or may not impact stuff that you're trying to do. And if things look like it's good to go, then you're just going through and saying, hey, looks good to go. Go ahead and continue on with that. Yeah. Questions about screening, what we did, any of the screening stuff that we did with this set? Yeah.
So how then, like the substantial missingness, you got it to be 17%. So is that like the 70 divided by
Yeah.
total number?
Yeah.
Okay.
It's
Cool.
just percentage of it. And thinking about it, again, like all this comes down to communication. How do I sort of convey, like I lost 70 cases? Well, it sort of depends, like on sort of is that big or is that small? It sort of depends on the situation, right? If I say 17% of cases had missing values in the original set, that starts to give me a better sense for sort of the magnitude of missingness.
So then would you change your N value?
Yep.
to-
Yep.
Okay.
And so you see right under there, after we get done with accuracy and plausibility, say cases with missing and plausible values removed, N equals 334 for the whole set.
Okay.
So what you're doing is this is just you telling me, this is what I did, this is what I did, this is what I did. And then I can go through and say, hey, looks good, or look at this a little bit more closely, or explain a little bit more about this, that type of thing. Other questions? All right, so we've screened our data, right? And we're pretty excited about that. There's a lot of time and effort, probably more than people will typically put into a single sample T, but that's all right, because we're all responsible investigators. Time now to go through in our sample of 334, actually run our tests, okay? And this is gonna be really quick and easy. We're gonna go to analyze. We're gonna go to compare means. We go to one sample t-test, okay? And in our one sample, our test variable is just our IIP 32. We're gonna drop this over into that, okay? And then what we need is we need to compare it against our test value. Someone remind me what the test value is for this problem. What are we comparing to? Amanda, I see you looking back through slides. You got it? Yeah, to a
Our undergrad is compared to
normative sample. What was the value for the normative sample?
mean of 25.
Mean of 25. Yep. because that's what we've got. So we're saying like, is there some relation between accident exposure and sort of interpersonal difficulties where we would expect maybe that our trauma survivors in our group to maybe report a higher level of interpersonal difficulties than what would be expected just from the general population. Okay. And so we know that based on this development paper, we're saying that in the development sample, we're saying that the test value is 25. This is my value under the null, right? And I'm going to keep estimate effect sizes checked here. I'm going to hit paste. And so I can see down here for my in my syntax, and just go through and run this command. And this is what I get. And again, this is all in hopefully you're following along and saving this, but this is all in handouts that sort of are again uploaded into the class WILE courses page. But this is what we get. Okay, so we start at the top. Always look at your descriptive statistics up here. This is going to make sure that you're running this on the sample that you think you're running it on. Okay, so we've got a sample of 334. Here's my mean. Here's my standard deviation. Okay, this shouldn't be anything news here, but I'm just making sure that I'm running it on this full number of people that I think I'm running it on. Okay, if I go down to my one sample test, okay, here I've got a t-statistic of 13.5. How do I feel about that statistic? Where does that t-statistic fall in the range of t-statistics? Yeah, it's massive, right? You think about t as being analogous to a z. If I had a z-score of 13, that would be a ridiculously large number, right? So here's my t, 333 degrees of freedom. Remember, our degrees of freedom here is the number of people in my sample minus 1, because I lose 1 degree of freedom. So I got 333 degrees of freedom. My two-sided p-value, because we're doing two-tailed tests, p less than 0.001. Here's my mean difference, and then my confidence bound around the mean the difference score here. Okay, now this is so SPSS is giving you this is the difference between what? What do you think, Elizabeth? We got 14.9 is my difference. What does that difference represent?
I initially kind of took it at, and I'm wrong, but my thought was that showing kind of the main difference. One subject scores the next subject score. But I thought that was really high. But I know that's not right.
So what is my test looking at? It's comparing what to what?
That's exposure.
Uh-huh.
So, given a stressor, our interpersonal functioning will fluctuate by potentially 13.5.
Okay, so conceptually, we've got what we're saying is that we've got a sample of trauma survivors, and we're interested in whether or not what their IAP scores look like relative to who. Yeah, just a regular population, right? So if my value under the null was 25, and where did 25 come from, Amanda?
It was the
Yeah, the measure mean from the development sample, big sample, 800 people, whole area, and sort of on average, people just in the general population, this is their score. This is the score we would expect for the IIP. But now we've got a very specific sample from a very specific population. These are trauma survivors.
Are you saying then that these, given a stressor, exposed to stress in the population in general, and then this kind of like PTSD group, and they're exposed to stress, the PTSD group, that they're around like the 13.5
that's the assumption, right? We're saying, so the mean difference here is 14.9, right? So this is if I take the mean of my sample, which is 39.9, and I subtract that from my reference value is 25, that's where that difference is coming. I'm saying that based on my sample, I'm expecting that to find college students exposed to trauma to be scoring about close to 15 points higher than the general population on this measure, okay? With confidence bounds, sort of my estimate is about 15 points, but based on the data that I've collected, anything from about 12.7 to 17 points higher would be reasonable guess based on the data that I've collected. Okay. How are we? So what are we pulling from this? What might we conclude based on what we found here? What's that now? Okay. What might we start to infer about the potential impact of trauma on interpersonal functioning? And to be clear, this is higher scores are indicating higher levels of interpersonal problems. Yeah.
If those in the trauma population have higher levels of interpersonal problems than those in the general population.
Right. Because if we say, hey, if we just look out at the general population, we see an average IAP score of 25. This sample, which is a big sample of 333 students with trauma histories, their scores about 40, right? That's a huge difference, right? If we look at, and so now if you were doing this by hand, you would probably calculate a confidence interval around just that mean value. It's the same thing as this. This is just, it's the same interval. Sort of your plus or minus will be the same. This is just calculating the confidence interval around the point estimate of the difference. The same bounds are going to fall up to here. They're just going to be sort of adjusted for that, right? And so we're saying SPSS is telling us that on average, we're expecting, so our data would support anything from a 12, say a 12.5 point to a 17 point increase in IAP scores in among student survivors relative to sort of members of the general population, right? So what I might do is start thinking about, hey, maybe trauma exposure does have an impact on interpersonal functioning and interpersonal problems sort of within this population. Okay. So one thing, remember that for one of our recommendations for thinking about p-values as a graded evidence for the incompatibility of our data with the null hypothesis, right? P equals less than 0.001. We kind of truncated off, and this is conventional reporting. But in SPSS, if I go through and I double click on this, I get a value of 1. We'll call it 87 times 10 to the negative third. No, that's not it. That's much bigger than that. I'm going to take this and I'm going to paste it into, shut up. What are you doing? Oh, I don't. What the hell? Unbelievable. Never mind then. Just do it here. All right, well, what you should be able to do, I'm not sure what the hell this computer's got going on, but you can take this value here in the P. Okay, whatever.
Yeah, I've taken a copy of that to the negative 33.
Okay, thank you, Matt, for not letting me just sit up here and drown trying to figure this stuff out. So whatever. So we've got something to the negative 33rd, right? So going through and reporting that, because that's a very different number. Okay. If we're thinking about the extent to which these data are inconsistent with the null hypotheses, 1.386, something like that to the negative 33rd is a very different thing than this, right? And so for this class, what I'm going to ask you to do is use that exponential notation to go through and report the p-values that are actually being sort of that are reported in there, because it just thinking about tests in terms of evidence against the null. Okay. Questions about this? Yeah.
Question about the.
Yeah.
So if instead of having like increased difficulty with interpersonal problems like our sample does here, if we're kind of in reverse, we may have fewer interpersonal difficulties, show up as negatives.
Yep. Yep.
Like still positive values. So we just have to.
Yeah, you just need to be, I mean, what you would want to do is just have some situational awareness, like look at sort of what your mean is relative to what the what your reference value was. What SPSS is doing is it's taking sort of the sample mean minus the reference value, which is sort of the formula, but you could switch it around. It would just turn things around. Sign is often arbitrary. It depends on who we're subtracting from who. But yeah, just making sure that you know, looking at your mean versus the reference mean, seeing that this is increased. But if people with trauma histories were having less interpersonal difficulties, we could just go through and make sure that our interpretation is consistent with what's actually going on. Okay, good question. Other questions? Okay. Now, other thing that we would normally do, right, in earlier times is maybe go through and want to calculate a confidence, or excuse me, an effect size for these data, right? Effect sizes for independent sample t-tests are pretty easy and straightforward. When we start to get into other analyses, effect sizes start to get a little bit complicated because there's a number of different ways that we can go through and calculate a standardizer. Here, we're just going to take D is equal to my mean 39.85 minus 25 over, what do I standardize my my effect size with? My standard deviation, right? So here we've got 20.092. Okay. We go through and calculate that. It's going to give us a value of 0.739, right? Call that 0.74. Can someone give me a interpretation of that effect size? Yeah. Not quite, actually. 0.8. 0.8, but that's all right. Cohen told us not to use those benchmarks, large, medium, small, as sort of doctrine anyway. What would be maybe a literal interpretation of this effect?
Gives her like trauma is a pretty good thing. Like that's involved in our.
Well, maybe, and that's kind of what we might work through in a discussion in terms of what we could infer from these data. What about this? So an effect size. This is just a measure of effect in what units? Standard deviation units. So I could say, based on my point estimate of effect, that my the sample mean that I've seen here is how many standard deviation units are they scoring above my reference mean? What's that?
About 3/4.
About, yeah, close to 3/4 of a standard deviation. So my sample is showing about 3/4 of a standard deviation above my reference mean, right? Now I don't have my population standard deviation. All I have is my sample standard deviation, but still that's a pretty sizable effect, right? Now my t statistic is massive, right? And my p-value is infinitely small, right? But what's going on in driving that, the size of that t statistic and that p-value? Go for it. My sample size. I've got a huge sample size, right? Remember that the only thing that this hypothesis test is telling me is it's saying, is this value different than 0, right? Or is it different than 25? And I've got an incredible amount of evidence that says, yeah, it's not 25. But it not being 25 is not terribly useful in terms of sort of what I'm wanting to understand. This effect size is saying, yeah, we're approaching, so we got a medium effect, but about 3/4 of standard deviation above the mean in terms above the reference mean in terms of interpersonal problems. And if we want to go through and pull in our confidence bound, we can say that our data suggests about a 15-point increase in IEP scores, specifically among student trauma survivors. But data are going to support anything from about 12.7 to about a 17-point increase. Right? And if I work with this measure quite a bit, I might say, wow, that's quite a bit larger than what I would have. That's a pretty sizable increase. Okay. Last thing we would do here is go through and we could calculate our S value is going to be the absolute value of the natural log of P over the natural log of 2, and our Bayes factor bound be 1 over negative E times P times the natural log of P. You have to have your scientific calculator out to do that. And we've also got a p-value here that is very, very small. So doing that on the board wouldn't make a whole lot of sense. But what I'm going to have you all do is streamline things eventually. Create yourself a nice little Excel calculator where I can go through and plug in, probably in this, if I don't know why this computer isn't letting me copy and paste anything, but if it was, I could take the p-value and copy it from SPSS and then drop it just into this field where it's gone through and calculated things for me. Or what I can do is I can take my t-value, which is 13.508, oh, is this still trying to make me sign up for? What's that?
Did it ask me to like log into your Microsoft account?
Looks like he is.
Oh, you're all right.
Yeah, here. No, don't want to. Okay. All right. Anyway, we go through, drop this in, and go. I figure this out. If we were to do this, we would go through result in an X value through the calculator of 126 and a Bayes factor of 3.4 times 10 to the 35th. Okay. So overall, based on these data, assuming that sort of the null model and everything else is sort of true, someone tell me what that S value, someone give me an interpretation of that S value. Yeah, Amanda.
That would be probably the comfortable.
This would be the sort of the evidence against the null in these data is about the same as we would expect as evidence of fair going following 126 consecutive heads. That's definitive, right? Functionally, these data functionally can exist if the true population IAP score for university trauma survivors was 25. I mean, it's basically ruled out essentially, right? Same thing, my odds for my upper bound my base factor 3.4 times 10 to the 35th, like that's a massively huge thing, right? So basically, these data are functionally completely incompatible with pulling the sample of 334 from a population having a mean IAP score of 25. It just functionally can't happen, right? Yeah.
That's just directly reflecting the p-value.
Yeah. And so, again, could I, if the true population sample was 25 for undergraduate trauma survivors for the IAP 32, could I pull a sample of 5 with a score of, was it 40? Maybe,
Yeah.
right? That would be considerably less evidence against the null. Probably unlikely, but it could. But as soon as I get up to 300, over 300 people, to have something that would be that far, that discrepant of a sample, you know, if we're looking at assuming a null distribution of mean equals 25 with a sample of 334. If this is the distribution of sample means, pull a sample of size 334 from this distribution of mean of 25 and end up with something with a mean of 40. It's functionally way out there, right? That's what that's saying. So again, we can, I know we've crapped on null hypothesis testing a whole lot, but if we've got something like this is pretty convincing evidence. I'm pretty sure that probably the average IIP 32 score among university trauma survivors is probably not 25. It's probably quite a bit different, right? So my best guess is about 40. This is also consistent with what we know about trauma and sort of impacts on interpersonal functioning and things along those lines. So we can take all this evidence. Now we can criticize sort of the sample and sort of the sample's probably not random, but we know it's not random. Sort of the extent to which it's representative, a lot of that type of stuff, but it would probably be hard to sort of square this with, yeah, basically undergraduate trauma survivors are about where everybody else in the larger population is. Okay. Questions about this? All right. So if we go back to our single samples test here, we go through, oh, yeah. And so our Cohen's D, okay, this is basically exactly what we calculated here for our point estimate, right? And here we're getting a confidence interval on our effect size. That's kind of a complicated procedure, but awesome that SPSS is doing this now. Again, I don't know why it hasn't up to this point, but it does. So this is nice. We got Cohen's D, and then we've got a Hedges correction. We'll talk about that in a few slides, what that is. So down here, it's nice. I'm still going to have you create an effect size calculator. It's going to look something like this, right? This is nice and a handy tool for you to have in case, so you can just plug in information and get effect sizes and things along those lines. But SPSS has now streamlined it. You're the first group of folks who have come through and had this at their capability. So that's going to streamline things for you, so you're not having to crank everything out by hand, right? So going back to our original set of things. So going through null hypotheses in words, right? Mean score for the IAP 32, mean score for IAP 32 interpersonal difficulties in the larger population of undergraduate survivors is 25, right? And technically that shouldn't be mean, that should be mu there because we're talking about population effects, but we'll take a note of that. In statistical notation, that's pretty easy. Mean IAP equals 25. Alternative, this is not 25. Okay. Confidence bound. So this is our confidence bound around the mean difference. We could also, so that margin of error, that plus or minus that you were all working with, it's the same if we were to put it around the point estimate. So just make sure that you know what you're calculating your confidence bound around. Here's my t statistic. Here's my p-value. Here's my effect size. Here's my S value, right? For these data evidence, give the null hypothesis of population mean of M25 on the IAP 32 in undergrad trauma survivors is similar to that, to observing 109 consecutive heads and tosses of a hypothesized fair coin. That didn't match up to there. Something went weird, but anyway, so to just focus on the sort of kind of what we're doing and how we're interpreting this piece of things. Same thing with the Bayes factor bound down here. Okay, so we're just kind of putting it together. So basically, walking through, providing interpretations, sort of recognizing our statistics and what they mean. And here might be an example of a write-up. Okay, so we're saying this first piece here, like you can have this or not, it's going to depend, just kind of orients you to kind of remind you what you're doing. Single sample t-test was used to compare interpersonal difficulties in trauma exposed undergraduates relative to normal scores from adults in the general population, right? This is kind of nice. It's just helping me sort of remember kind of what we're trying to accomplish here. The null hypotheses for these analyses posits no difference in interpersonal difficulties in undergraduate survivors relative to members of the general population. This second paragraph, don't worry about that. This is just screening stuff. We've switched this over and we're now doing this other screening. I mean, if you were to put it in paragraph form, might sound something like that, but don't worry about it. Just use those, your screening stuff. But here down getting in the meat and potatoes. So we're saying trauma exposed students in the current study evidenced a mean IAP score consistent with 3/4 of a standard deviation increase in interpersonal difficulties relative to scores in the general population, and then putting in our thing, right? Just saying, hey, this is sort of the magnitude of the effect. Population differences in trauma-exposed students to normative adults range from 12.69 to 17.01, found to be compatible with responses. A single sample t-test identified data is highly incompatible with a null model specifying a population average of 25 in trauma-exposed undergraduates. And then we've got sort of all of our statistics here, okay? What did I not say at any point in sort of this piece of things? Yeah, I didn't, because you don't, was there anything that we missed in here? No, we don't, like, we make a good argument that sort of identifying things as statistically significant, it's sort of a crutch, right? It sort of takes a burden off of me to try and explain kind of magnitude and things along those lines, right? And we're trained to do it, and it's easier to do it, and so it's easy to fall back on. But for the write-ups that we're doing in here, and so what you do on sort of in your labs and research and things like that, I have no sort of ball in, right? But for here, just wanting you to try and sort of think about putting things together without having to say something significant or not, because I know what it is. Because if you just report the p-value, like I'm able to know whether or not something is greater or less than 0.05. So just trying to tie this stuff together into something that makes some conceptual sense. Okay. Then down here at the bottom, this is where we're trying to pull things together, right? So sure, this is what's going on. What does this mean for the question at hand, right? So we say results of these analysis offer support for moderate to large elevations in interpersonal difficulties among trauma-exposed undergraduates with some level of event-related distress. Say while compelling, missing lists in the larger setting produce the possibility of bias, which could in turn have estimates of interpersonal dysfunction, right? So just based on my screening, if I don't know why we're missing those 70 cases, I'm not sure why, right? It's possible that those 70 missing cases are people who just had really low IAP scores that were systematically gone. So unless I got a handle on why those were missing, I need to kind of take that into account, right, to what may be going on. We say it's also important to note that participants in this study were substantially younger, more predominantly female, and more highly educated than respondents in the normative community sample. As such, we're unable to determine for this study where elevations IAP total scores are associated with trauma exposure or some other variable, okay? So thinking about, sure, we think that this probably at least is associated to some extent with trauma, right? It would be consistent with theory and what we understand in terms of trauma as its impact on people. But our subsample was very different in a lot of characteristics from the other samples. So maybe highly educated undergraduates are just sort of generally disagreeable. It is possible, I don't know, right? But what we want to do is sort of recognize what we can and can't say. So we have some evidence for, right? But also recognizing that the background characteristics of the people who we've pulled are different in a lot of ways from our reference sample, in more ways aside from just then trauma exposure. And so wanting to sort of recognize alternative hypotheses or alternative explanations for sort of what we've got here. Okay. So questions about how we've kind of gone through and taken this whole hypothesis testing stuff and tried to kind of pull it together. Okay. Yeah. Emily.
So this is probably more of a conceptual question, but is there the case where we do not get a significant value for results? Like, do we need to go through kind of extra steps, or do we just need to go report like three-word thing?
Well, I mean, yeah, I mean, if there's not much to be seen there, then we probably wouldn't spend as much time sort of going through and talking about things. I mean, anytime we get a null result come up null, we're just saying like, I don't know, we just don't have, not saying that there's not anything there. I just don't have data to say whether there is or there's not. That I might take a look at confidence bound and say, based on the data, plausible estimates for the population range from somewhere from this, which is much lower to this to much higher. So at this point, so I might probably comment on maybe why I couldn't sort of make a strong statement about things. Like, well, because we had 15 people in the sample, so it's hard to say what's going on, right? So comment about that type of thing. Yeah.
So because our methods are never going to be perfect.
Well, I mean, sure, as long as it's meaningful, right? Like, what I want you to just tack on the gratuitous, but more data collection is needed, because that's always the case. So it doesn't actually add anything new to the conversation. What you might say is for this, right? What you might say is future studies could look to pull samples that are more representative of the larger population, if to further clarify the specific impact of trauma exposure on interpersonal functioning or something like that, right? Just saying like, oh, hey, we need more studies is not a useful or helpful thing. If you tell me what specific type of thing might be useful in helping me clarify that, that would be pretty good. Other questions? Okay, cool. So, okay, so this is obviously no one's going to tolerate that in a for a single sample t-test in a write-up in a publication. This is just an example of something that's maybe just a little bit more streamlined that sort of could go in a results section. That would be kind of based on what we're doing, but sort of again, sort of the purpose of these assignments is not to publish them, to let me know you have a good conceptual grasp of what's going on. So sort of something that's a little bit more sort of full and sort of talking about some more nuanced stuff is what would be preferable. Oh, okay. So again, sort of quote from this Wilkinson article, thinking about credibility, generalizability, and robustness, right? Like, so thinking about, as we're pulling this together, like, is the sample credible? What can I infer from this? This effect, is this likely to replicate? Given sort of this? No? Yeah, for sure. We have huge, massive evidence. This isn't something that just kind of hanging out, like it snuck on the other side of 0.05. This is something like, these data are functionally incompatible with a null value of 25, right? So we're pretty, if I wanted it, sort of, I would feel very comfortable moving forward under the assumption that undergraduates exposed to significant trauma are experiencing some increased level of interpersonal difficulties relative to the general population. I mean, I'm pretty comfortable with that. Now, there's other stuff that could be going on, right? In terms of the stuff that we had talked about with respect to sort of how our sample differs from other people. But if I'm only interested in undergraduate trauma survivors, I'm pretty confident that this is a value that's very different than sort of what we would see in the general population, right? So wanting to think about, do my effects make sense within the context of sort of what I know about this stuff? And I don't expect you to be experts on all the stuff that we're going to talk about, just kind of thinking carefully about, okay, in general, what might I assume about this thing, and trying to pull that in together. All right, so this is good. We like this. But at this point, our Z statistic and t-test are comparing a sample mean to some unknown population, to some known population value. But as Josiah kind of alluded to earlier before we got into all of this, single sample Z and T often require more information that's generally available. It requires me to have some point estimate of something out in the universe, which I may not have, right? And what we're most often doing, or more commonly doing, is trying to compare two different groups, right? Two different samples drawn from populations with an unknown mean and variance, right? Sam, let's say you're running some sort of experimental study, looking at some psychophysiology stuff. You've got maybe a pathological sample or some sample of students that has some level of pathology and some students who don't, right? You don't know what the mean skin conductance is for that population or the variance, right? All you have is two samples that you are hoping that are reasonably representative, right? This takes us out of single sample t-test, right? So what we do is then transition over into our independent sample test. Okay? Our independent sample test, this is what we're using to look at differences between two populations. Okay? What we're doing is we've got comparison means from two unknown comparison of means from two unknown populations. We've drawn a sample from one unknown population, drawn a sample from another unknown population, and we're going to compare the samples, right? We don't care about the samples. The samples are just a means to an end, right? What we're trying to do is saying, is the data that I've drawn from these samples, do I have enough evidence here to assume that these were probably drawn from populations having some different mean, okay? And this is going to be kind of one of our most simple, straightforward experimental designs. Sample one, sample two. Do I have sufficient evidence to assume or to make a conclusion that these were likely drawn from populations having different means? So our null hypotheses with our independent sample T is that mean of population one subtracted from mean of population two is equal to 0. Okay, difference between the population means is 0. We're assuming alternatively scores were likely drawn from populations having equal means. Our alternative hypotheses, population mean 1 and 2 are not equal to 0. Difference to some non-zero value. Observed scores are unlikely to have occurred if these means, the respective populations were equal. If population means are equal, and I go through and I pull the mean of sample one, and I pull the mean of sample from population one, and the mean from population of sample two, and I subtract those two, what should I get? 0, or something reasonably close to that, right? What we're trying to do with our independent sample test is see, is that difference some value that's far enough different from 0 that we would say, yeah, there's probably something on these data. Okay. Again, is the difference in scores between these two samples sufficiently large to conclude that they were drawn from populations having different means? So our independent sample T's assumptions, once again, we're assuming our outcome our outcome variable is continuous. Observations are independent. Again, sort of no one's cheating off anybody else's paper. Everybody's sort of reporting their own scores. Distribution of sample means for each population is normal. Again, remembering it's not the data that we're looking at. It's the distribution of sample means that we're interested in looking at. We still want to screen to make sure that there's not weirdness going around that's going to throw things off. But our technical assumption is normality in the distribution of sample means from each population. Okay. And we've got a new one. We've got homogeneity of variance. Technically, under our classic independent sample t-test, we're assuming that the population variances, the samples from which these or the populations from which these samples were drawn, we're assuming that those populations have equal variance. Okay. Our informal assumptions, data don't contain outliers or extreme values that are going to start pulling that, dragging that mean around. And we're kind of assuming that we've got relatively equal samples across my two groups. Okay. Questions about our assumptions here? Yeah,
So the homogeneity of variance, how important is that?
hold on to that. We'll get into that. Okay. Other questions? Questions that are appropriate for right now. Damn it, man. Yeah. Okay. So we've got kind of this assuming equal sample sizes and sort of this homogeneity of variance, right? And then all of our ancillary hypotheses. They're always there in the background that we don't ever factor in because we know we violate this all the time, but we should still be thinking about this and specifically the impact this has on influence. For a formula for independent sample t-test, this is going to be, so technically our formula is mean 1 minus mean 2, subtract population mean 1, population mean 2 over standard error, the difference here. But population 1 minus population 2 is always going to be 0, or almost always going to be 0, and sort of what we're working with generally. So that goes away. And so we just got the difference in our samples over the difference, the standard error difference across our two samples here. So this indicating the standard error difference in our sample. Okay. Before we had the standard error of the mean, right? That was our standard error. Now our standard error reflects the expected difference in the sampling distribution of difference scores. So if I were to take here's pop 1. Here's pop 2, right? This is all individuals in population 1, all individuals in population 2. If I were to pull all possible samples of 50 and subtract those from all possible samples that could be drawn of 50 from this, and I would look and map out those difference scores, I would get a distribution of difference scores. This would be x1, x2, and so I'd have a sampling distribution of those difference scores. Sampling distribution of difference scores, my standard error here is looking at the standard deviation of this. Okay. I'm just looking at a different sampling distribution. Standard error is just this standard deviation of the sampling distribution of different scores of all possible samples that could be drawn from this, all possible samples that could be drawn from this. And so still an estimate of our standard error, or still a standard error estimate, indicates how well any my estimate of mean 1 minus mean 2 is going to estimate population mean 1 minus population mean 2. Just like anything else, it's just going to tell us how much deviation, how much jumping around should I expect? How close should I expect my estimate to be to the actual population value? How much should I expect my estimate to jump around from replication to replication, right? And it's going to be calculated similar to how we calculated things before, okay? Now, the thing to remember with our the thing that we had with our independent sample T here, we end up with two sources of error now, right? Before with our single sample test, we just had one sample to deal with, right? Now we've got two. And what we do is we find that we're approximating our mean value of the population in sample 1 with some error. And we're also estimating our mean value of population 2 with some error. And what this has done is now it's doubled up on our error. Our standard error has now effectively increased by a factor of 2, okay? Because we have to take both of these into consideration. So our standard error estimate for an independent sample t-test needs to take in both of these sources of error And so our standard error for independent sample test, what we get in the denominator is we going to be calculated as the square root of the variance of sample 1 for the sample size plus the variance of sample 2 for the sample size. Okay. And so just looking at this formula, what does this do, having to account for 2 sources of error? What does this do likely to the power of our tests? Yeah, it makes it a lot smaller. Okay, this is why between sample tests are oftentimes hugely underpowered, because basically we're relative to single sample tests where we just had 1 source of error, right? Now we've got 2, we're doubling that standard error. That standard error is now much larger than it was in the previous test. If I'm sort of dividing something by something that's twice as large, that test statistic is going to go down. It's going to be harder for me to hit those goals. So if we think about this, the variability of our difference scores. If I've got 2 randomly selected, thinking about the possible range of any 2 randomly selected scores that I can pull from population 1 and population 2. So blue here is population 2, red population 1. My range of population 1 range from 25, so down here to 7 to 95, so we've got a range of 70, right? In population 1. Population 2 ranging from, we'll say, 15 to 65, right? So I've got a range of 50 in there. If I go to the extreme, right, and my sample from population 1 is 95, and my sample from population 2 is 15, right? So the most extreme samples that we could get from these 2 populations, I get population 1 is 80 points greater than population 2. On the other extreme, if I get the highest score for population 2, it's 65, minus the smallest score for population 1 is 25, I get 40 points in the other direction. And so if I go through and map this out, so if I think about the possible deviation that I could get from these samples, and we're not saying it's likely, but it's mathematically possible to get anywhere from -40 or 40 points in one direction to 80 points in the other direction. This is a maximum of 120 points that could be sort of the full thing, right? So from a theoretical standpoint, given sort of whatever sample I'm getting from, I could get values that range anywhere from sort of a lot of points in favor of this sample versus a lot of points in favor of this sample. Consequently, if I add up the ranges of those 2 populations, it's sort of the total max difference that I could get in terms of the samples that could be drawn, okay? And so basically what we see is this standard error is an additive function of the variance in both of these samples. And so what we do instead of with our single sample test where our standard error was just the square root of the variance over the sample size, we have to multiply that by 2 and we have to take both of these samples into account. Questions about this? This is just kind of a peek behind the curtain and sort of why specifically we have to double this up and why our error starts to get quite a bit bigger when we're shift over to an independent sample t-test versus what we saw with our independent or with our single sample test. All right, but what happens if we have different sample sizes, right? What happens if my first sample is only 10 people, my other sample is 30, right? You got my second sample is 3 times the size of my other sample here, right? I also know that my large samples provide a better estimate of corresponding population value than my smaller samples do, right? And so if I've got big discrepancies in my sample, that starts to throw things off, right? Because I assume that homogeneity of variance is an assumption of my independent sample t-test, right? I'm assuming that the populations from which I'm drawing my sample have equal variance. So from a theoretical standpoint, should I be concerned if the actual values for the variance in my samples are different? From a theory standpoint. No, right? Because if in theory, if I'm assuming that I'm pulling from populations with equal variance, the fact that sample 1 and sample 2 have slightly different, or sort of have different variance estimates is sort of inconsequential because the underlying assumption of the test is that they're coming from populations with equal variance, right? But at the end of the day, these estimates are never going to be identical, right? And if I have unequal sample size, the smaller sample is going to exert a greater influence on the estimate of my total population variance. Because remember, my standard error here, I have to take my variance of sample 1 divided by n, variance of sample 2 divided by n. If I have the sample, if these two things don't match up, if these are horribly discrepant, what ends up happening is the sample variance of the larger sample starts to outweigh my overall estimate for my standard error relative to my smaller sample. Okay. What we end up doing here is we go through and we calculate a pooled variance. Okay. If I have unequal sample sizes, what I'm going to do is I'm going to create a pooled variance estimate where we're going to take sample 1, the size of sample 1, subtract 1, and then multiply it by the sample variance, plus sample 2, however many people are there, minus 1, multiply it by the variance of sample 2 over n1, sample 1 plus sample 2 minus 2. Okay. And what this is going to do then is for my sample with the more people, again, I'm assuming that these samples were pulled from populations with equal variance. I'm going to give more weight to the sample that's larger and presumably has a better estimate of my population variance than the smaller sample. Okay. And so basically what we just have here, my pooled variance is just a weighted average of the variances, essentially. So what we end up with here in our final formula for independent sample T is mean 1 minus mean 2 minus population 1, population 2, that cancels out over the standard error of the standard error of the mean difference. And standard error of the mean difference, we can calculate that as the square root of variance 1, or it's my pooled variance divided by sample size 1, pooled variance divided by sample size 2. Degrees of freedom for independent sample test is just going to be sample size 1 plus sample size 2 minus 2. So people see why this pooled variance starts at pooled variance. We're going to see pooled variance again and again and again and again. People understand why we can't just take the sort of the average of this and sort of calculate these out, why we're kind of weighing this out.
No.
Okay. So essentially what we've got going on, just go through and take a look at this. If this is my overall, if I'm just using sort of sample 1 variance divided by this, sample 2 variance divided by this, what we're doing is we're just adding these up and we're treating these as equally valid estimates of the population variance. When in fact, if I have a big discrepancy in my sample sizes, the larger sample, assuming that these are drawn from populations with equal variance, the larger sample is going to be a better estimate than the smaller estimate. But this isn't reflecting that. We're just sort of taking these both as sort of equally valid. So what we do then is instead we go through and we calculate the pooled variance. And the pooled variance is just the weighted variance, sort of weighted based on the sample size. So we've got sample 1 minus 1 multiplied by the variance of sample 1, sample 2 size minus 1 times variance of sample 2, all over n1 plus n2 minus 2. Sneezing into a mask. That's fun. We're just weighting this out. And so essentially what our pooled variance is doing is it's giving more weight to for my overall variance estimate, because my assumption of my test is that they're equal across populations. I'm just weighting that estimate more towards the sample with more people in it than less people in it. And then what I do is I just substitute that pooled variance for the variance of sample 1 and sample 2. So I've got the same estimate. I'm just taking that pooled variance estimate, dividing by sample 1, pooled estimate divided by sample 2 to get my standard error. All right. So why is it useful to know my degrees of freedom for these analyses? Where we start to solve mysteries. Okay. Sometimes when we're seeing a reading articles and papers and things like that. If we start to see that degrees of freedom jumping around for tests that degrees of freedom shouldn't jump around, what does that tell me?
If they have variables that they're not recording, or samples that they're not recording.
Yeah, should I have probably missing this that they haven't told me about? And so basically what these samples are doing is they're looking at different subsets of the population based on who they have information from. Reviewing a paper right now where someone reported degrees of freedom, thankfully, in a test that did not at all match up to what they had reported. And so you say, hey, you said that you have this. Degrees of freedom are saying this. Those are light years apart. Let's go through and check. I don't know if it could be, maybe it was a typo, maybe it was something gone backwards. I don't know, but it's worth going through and looking. Okay. If we don't have degrees of freedom, right? If we don't have our degrees of freedom right, what does that do? That impacts our distribution of our test statistic. And we don't know what the distribution of our test statistic is. What do we have? I saw Matt jump. He was scared. We have distributions, and we can't have any confidence in our actual sort of tests, right? Because we're comparing it to something that sort of didn't make sense, right? If I've got some distribution of a test statistic that I don't know what it is, then I start to lose confidence in my outcomes. Okay. All right, we'll finish up with measures of effect size. Raw difference across my two samples can be useful. Again, Sam, what's that?
I'm sorry. I got distracted by the camera. You said the degrees of impact.
It's just the degrees of freedom are telling me how many people were in each one of my groups in my total sample. So if I have, let's say someone has, they say, oh, hey, if someone's saying, hey, I compared this sample of 2 and this sample of 50 and this sample of 50, right? But then I see on the degrees for their t-test is 38. Does that square up? No. Like, I don't know, apparently for this test, you didn't have samples of 50 and 50. Because if you did, you should have 48 degrees of freedom. So you are running a t-test on different groups than what you told me you were, right? And so now I can start asking questions about what's going on with this. Or they say, oh, my degrees of freedom are 105. Again, that's not consistent with what we've got here. So you added some people into the mix. So you got to explain what's happening with this. These degrees of freedom are also helpful with calculation of effect sizes based on test statistics, right? So, and sometimes people won't report those, but if you know how many people are in each sample, you know how to calculate degrees of freedom, you can derive that for yourself. So it's just good for awareness of things. All right, so we'll pick back up with effect sizes for independent sample t-tests next week. And try and move through sort of the rest of this reasonably quickly. Okay, and then we'll work through some examples here. All right. So it seems like people have gotten a pretty good head start on problem set 3, which is good. Let me know if you're running into any problems with that running up towards the Friday deadline, although happy will probably send us problem sets, I don't know, later on tonight, because you like to be way ahead of schedule. I will go through and get those scores on your problem set 2s and back to you. You'll have them in your box by tomorrow. Did really well there. Just make sure that you're being precise with your language, kind of fleshing things out. But if you have any questions on interpretations, just let CJI know. Awesome. Thanks, everyone.
Thank you. Thank you. Thank you.
Yes.